So today's speaker, we are very lucky to have Huiwen Ju. She is an NVIDIA architect and solutions engineer, and she helps a lot of researchers like us who are interested in health science. Dr. Ju has a BS in physics from Fudan University. She also has a master's in computer science and a PhD in computational neuroscience from Georgia State University. And today she will be talking about the Clara software created by NVIDIA and how it can help us accelerate our health research.
All right. Thanks, Andy, for the introduction. Thank you so much. And thanks for everyone coming to this session. I'm very excited to have this opportunity to do a presentation to you to introduce NVIDIA's interesting tools. Let me start sharing my screen. All right. Okay. Okay, let's jump right into that. So the title, NVIDIA Solutions to Accelerate Health Research. So again, my first name is Huiwen. Hui as in Chip Hui, very popular cookie, right? So it's Huiwen. Okay, so this is the agenda I put together. Okay, let me minimize this window a little bit. Okay, it's better. So first, I'm going to give you a high-level overview of where we stand in the AI era, and then how NVIDIA is trying to contribute to this AI community and support the whole AI community. And then also, what is NVIDIA's solution for healthcare and life science. I'm going to lightly touch on almost all the tools on NVIDIA's healthcare dedicated platform called Clara. And if you have any questions, we can definitely, I'm very happy to do follow-ups with you. Maybe we can schedule a virtual meeting to dive deeper into each of those tools. Today, I know the major audience are from College of Health, so I really want to focus on how NVIDIA is accelerating this domain called digital health. So specifically, I want to go through a sequence of AI-based tools which are built on top of each other. Actually, all those technologies, large language models, retrieval augmented generation, and also more recently, this one is very popular AI agent, and how we can build on top of a very general AI agent to make it a research assistant AI agent. And then how we can further augment the AI agent to give it a human appearance, to give them the human voice, give the human-like minds to help us tackle more complex problems. So I'm going to introduce a NVIDIA solution called Digital Human. Essentially, it's just an avatar. And after that, hopefully we can then stand on be on the same page, know some basic common concepts, and also NVIDIA's current solutions. I actually compiled a list of recent, I would say, like most significant research papers in this domain, and to try to inspire all of us to think about how we want to leverage LLMs in our own health research. And also we will mention some real world use cases from like startups, biotech companies, and also some other industry companies to just see at a high level what they're trying to do, what is coming up in the future of leveraging LLMs in health research. And after that, then it's the hands-on time. So I remember we asked you to bring your laptop to this session, right? So we're gonna, first I will like demo several most interesting AI models in the web browser by going to NVIDIA's AI website. It's actually the NVIDIA's AI catalog hosting lots of state-of-the-art AI models there. Then I hope you can play with those and interact with those AI models by yourself to see their performance by yourself. finally, I will give you a slide listing some learning resources if you want to further your understanding about the current AI technologies, to learn from the most brilliant minds. We have many tutorials, recordings, online courses, etc. And finally, maybe for the very last 15 minutes, we will open up the Q&A. So I will answer questions from the in-person attendees, and also we will look into the chats over Zoom, and then answer questions from there as well. Okay. Yeah, so I do hope you can keep your question for now, maybe take some notes, and then let's wait for the final Q&A session to ask questions, because I have prepared many slides, and I really hope to go through it first to build a common understanding for all of us. Okay, so first, the overview. Where we are in the age of AI, well, the AI revolution is here and accelerating. So we have witnessed the explosion of lots of perception AI. Remember those open ImageNet challenges for computer vision? Like people can build very powerful visual models, right? Computer vision models to distinguish a photo, whether it's a cat or a dog, and also in other modalities like speech recognition. When I'm speaking, it can recognize the words, transcribe the audio into some text, right? So this is the perception AI. I think we have already kind of passed it. And then after that, we have this generative AI. So generative AI can help us to generate something new, right? Because they have been trained to identify and really learn the pattern from real world data. And then based on that kind of knowledge, once they learn some kind of distributions, probabilities, they can generate something new for us. For example, we can type in some description, and then it can generate a new digital marketing video for us. And also, I myself have been using ChatGPT. I really love that. So those like ChatGPT, Claude, if you're using it, or Perplexity, those LLM-based applications, they are all fall into this category, generative AI, because they are generating new data, right? And they can be in different kinds of formats. Maybe it's text, maybe it's audio, maybe it's video, maybe it's image. And then here, I think we are here now. Lots of people are developing for agentic AI. And now we are at a point where the those AI models are becoming so powerful that some of them actually have this human-like reasoning capabilities to help us break down a very complex problem into several steps. Kind of take this divide and conquer approach, and then it can call individual tools to help us solve each of those smaller problems, and then put together a end-to-end solution for us. So agent, this concept is actually not that new. It has been for a long time. It's just those AI models, especially the AI models that can reason together with the humans, are empowering those new generation of AI-based agents. So you can imagine we can use them as our coding assistants, coding co-pilot, lots of use cases. And then I think we're still we are in this phase, actively developing for those kind of powerful physical AIs as well. So when we're talking about physical AI, you can think about those autonomous systems like self-driving vehicles or surgical robotics that are helping our surgeons to do surgeries. So those AIs, compared with, for example, Gen AI, generative AIs, they have this capability. They actually gained a very good understanding about the real 3D world, and then they understand the physical laws of the real world, so that they can actually navigate on their own within the real world, and then interact with the real objects in the world. And so I would say we are currently at the active development stage of those two kinds of AIs. Okay. So how NVIDIA is trying to contribute and support of this AI community? Well, this is actually one of my favorite slides called NVIDIA 101, because I really want you to know that NVIDIA is always taking this full stack acceleration approach to support any kinds of computing problem. And AI is just one of those computing problems that NVIDIA has invested a lot, and NVIDIA definitely has the capability to make lots of previously impossible things to happen. So by full stack, I really mean NVIDIA tried to accelerate all levels of the computation. So from the chips to the computing systems, like you guys are going to have a supercomputer installed very soon, right? And then also NVIDIA invests a lot into software stack as well, like acceleration libraries. Those libraries, for example, cuDNN goes into those popular AI training frameworks like PyTorch, TensorFlow, right? And then on top of that, NVIDIA builds domain-specific application platforms. For example, Clara is one of them, which is focusing on healthcare and life science. And one of the latest technologies from NVIDIA's side to enabling AI is called NVIDIA NIM. So NIM is an acronym. It stands for NVIDIA Inference Microservices. So essentially it means NVIDIA is wrapping up and also optimize, maintain those most popular and also state-of-the-art AI models, wrap them up, make them into a container, essentially a container, so that anyone, as long as you register for a free NVIDIA developer account, you can download this container and then run this model and deploy it anywhere you want. It can be on your own workstation, maybe in the cloud or on the supercomputer. Okay, so it's really, in my view, it's the easiest way to get your hands on those state-of-the-art AIs and then start using them, start leveraging them. And like I mentioned, we recently have those reasoning model names. So we wrap them, NVIDIA optimize them from the open source community, maintain them, rigorously test them, make sure they get you the best performance, not only by performance here, I not only mean the accuracy, but also mean the throughput when you do inference, when you deploy it. So you really want to get high throughput, low latency inference performance. Yeah, and then we understand that those off-the-shelf models probably cannot meet every user's needs. So we also have NVIDIA NeMo. It's a framework, and also it released lots of microservices like listed here to help you to customize your own AI models. Okay, so for example, Curator can help you to curate your own training, fine-tuning data set. Customizer can help you to further fine-tune the models, maybe just several layers. Yeah. And then after that, like I mentioned, we are already in the age of agentic AI, right? So NVIDIA also put together some blueprints to showcase how to leverage those LLM, how to put them into realistic workflows so that you can use those blueprints as reference workflows. And then based on top of those blueprints, you can modify it, you can add more magical source onto that, and then make your own applications. So essentially it's just give you a leg up to help you get up to speed faster. So for example, we recently released lots of blueprints for different sorts of agents. Okay, so yeah, we are going to see some of them. Okay, so that is what is NVIDIA doing in general. So let's now shift our gear a little bit to see what is NVIDIA's Clara Platform doing for healthcare and life sciences. So it has three major focuses for now. One is digital biology. Think about we want to accelerate the discovery in the genomics, proteomics space, make drug discovery even faster, and also make the analysis of genomic sequencing data faster. That falls into digital biology. And then we also have digital health. So we know we have tons of healthcare related data, right? For example, EHR data, lab records, or other kinds of data. So we want to leverage them and then extract new insights, new patterns from them. And also we might want to build some agents to help alleviate the burdens of some researchers and some physicians, right? And finally, healthcare, the Clara platform also supports digital device development. So think about those surgical robots. Think about developing medical imaging AI so that once they're matured, we can deploy it onto some edge devices like ultrasound. So those are the three main focuses. But today we are gonna mainly dive deeper into digital health. Okay, so on this healthcare dedicated platform called Clara, we have these tools. Parabricks is for secondary genomics analysis, give you much faster performance compared with the CPU-based counterparts. BioNeMo is a framework for training, fine-tuning, and also do fast inference for biomolecular language models. So I'll give you an example. For example, AlphaFold 2 is also supported out of box. And then, so moving towards digital health, we have NeMo. It's a natural language training, fine-tuning, and also inference framework. So yeah, we were going to see some of the already trained LLMs by using that framework, and we're gonna interact with those LLMs today by ourselves. Okay, and then for medical imaging AI, if you're already using PyTorch and you want to build some AI for medical imaging, then Monai is a good option to look into because it's a PyTorch extension. So, and it's dedicated to medical imaging. So already builds many useful APIs so that you can save tons of engineering effort. And then if you want to do federated learning, for example, if you want to train an aggregated model together with your friends, collaborators from other institutes or other universities, then you can leverage NVIDIA's NVIDIA Flare SDK framework to build a very robust real-world federated learning project. And then moving towards digital devices, Holoscan is a accelerated sensor processing platform for NVIDIA, also supporting AI use cases. So think about when we want to deploy some AI models, for example, like ultrasound or other like devices, we want to extract some insights very fast, just at the patient side, right? And then for robotics, Isaac actually just 1 month ago announced to have some new modules supporting developing support for developing healthcare related like surgical robotics. Okay, so I'm gonna elaborate a little bit for each of those tools now. Again, happy to have follow-up conversations with you guys if you have more questions. So just this one is just want to show you what is available from NVIDIA's Clara platform. So in the genomics research space, NVIDIA is very ambitious. We want to support short read, long read sequencing data, and also want to support analysis for single cell and also spatial omics analysis. So today, if you are using Broad Institute's GATK suite of software, then NVIDIA Parabricks is a GPU-accelerated drop-in replacement for lots of GATK's tools. So it covers alignment tools, like the recent added one, pan-genome alignment tool like Giraffe, but also the more traditional ones, VWA-MAN, and also for long sequencing data, Minimap 2, and also for RNA sequencing, we have STAR there. And we also offer off-the-shelf accelerated high-accuracy variant calling, those variant callers as well, like deep somatic, deep variant, and haplotype callers as well. Yeah. So essentially what gives you like up to like 100 times a faster speed compared with the CPU counterparts. Yeah. And by doing something quickly, it can really make a real world impact. For example, it can make those nationwide population level, like human genome studies, like the one carried out by Japan, very possible. So they essentially cut down the alignment time from over like several hours to just several minutes. And similarly for Regeneron, which is a genetic center, they sequence lots of exomes from UK Biobank, and then they were using NVIDIA Parabricks to do alignment and variant calling. And by doing so, they also told us not only it's so much faster, like from 1 hour per exome on CPU to like 5 minutes per exome on GPU, but also they saves over 50% of their computing expense in the cloud. Okay. So yeah, we do have lots of success stories in this domain. Okay, moving forward, if today you're dealing with single-cell RNA sequencing analysis, then probably you are doing a pipeline like that. You start with a very large cell gene matrix. You go through all those kind of steps, and everything in those green box are the tools that you're using every day. And for all of those tools, you can leverage the GPU accelerated drop-in replacements from the library called Rapids. So Rapids is a GPU-accelerated open source data science framework. Okay, so if we have some benchmarks, you can see here when comparing a GPU acceleration one with the CPU counterparts, you can see you can get significant acceleration there. If you want to learn more about that, we have excellent tutorials like in Jupyter Notebook format for you to explore. And yeah, because of those great performance there, it really inspires some developers in the single cell verse, SC verse domain, developers there to leverage those Rapids APIs to build their GPU accelerated drop-in replacement for the ScanPy library. So you can see it makes the dimension reduction algorithms and also visualization algorithms like UMath super fast for very large data sets. And here is the astonishing speed up when comparing with the CPU part. Okay, moving to BioNeMo. BioNeMo is a biomolecular language model framework. You can use BioNeMo framework to scale up your training. Okay? Because we know like scaling up AI training is a non-trivial thing to do, and it requires lots of engineering effort. And NVIDIA has like over the past decade, NVIDIA developed those kind of technologies, and now we are putting them into this framework to help researchers in this domain to easily leverage those scaling up techniques to easily apply it to their own language model training. And then, if you just want to use the off-the-shelf language models like AlphaFold 2 to do some large-scale screening for your research projects, then you can just try out those BioNeMo NIMs, because NIMs, remember, it's NVIDIA Inference Microservices. It wraps up everything, packages it all up, so that you don't have to worry about anything. You just need to download it. All the environment is there, all the acceleration layers are there. You just need to deploy it with a beefy enough NVIDIA GPU and then run it. Okay, so just want to give you some sense about what kind of models are available from BioNeMo. So roughly it can be categorized into several classes. One is for protein. We have models for protein generation, getting meaningful embeddings, and also protein 3D structure prediction. And also for small molecule, we have small molecule generation, representation, and also docking your target protein with a potential small molecule as a therapy. And also in the genomics domain, we have foundation models supported for RNA, DNA. So the last bottom line is for those kind of things. Okay, so if you're doing medical imaging AI, then please look into MONAI. MONAI stands for Medical Open Network for AI. So it actually has lots of sub-libraries. So the way we imagine you can leverage that is like this. So maybe you have a problem at hand. Maybe you want to first look into MONAI Model Zoo to see if there's already some similar models or foundation models. You can just stand on top of the giant's shoulders, right? And then start from there to fine-tune your model, for example. And then you can use MONAI Core to do the training. Remember, MONAI Core is just essentially a PyTorch extension for medical imaging AI. And then so that actually assumes you have your label dataset, right? So if you don't have your label dataset already, you only have your raw dataset, then maybe you can use MONAI label to quickly annotate your raw dataset with the power of AI. And then once you have your mature model, you can use MONAI deploy to make it into a ready-to-run application and then deploy it anywhere you want. And so what is the latest in this medical imaging AI domain? Well, foundation models. So MONAI releases the source code and also tutorials about how to train certain foundation models, both in radiology and pathology domains. And also more recently, lots of people want to build multimodal models in this domain. For example, some VLMs. Maybe you just throw a VLM, a CT image, and then you can ask the VLM to give you some general understanding about that CT image. Ask the VLM if there's any anomaly there. So yeah, we released all of them. So please take a look at them. Okay, so maybe you want to build a even more generalizable AI by collaborating with your friends or collaborators at other institutes. Then, for example, you want to collaborate with other like hospitals or other departments of public health from other universities. Then you can leverage NVIDIA's the FLAIR framework. So it doesn't have to be training a deep learning model or AI model. It can be like, let's do an aggregated big data analysis together, right, to extract some fundamental understandings from that. So it's also supported. So learning here from NVIDIA, it doesn't just mean deep learning. It can be any kinds of work you want to do. So like during COVID, NVIDIA collaborating with over 20 different sites across the globe and train an aggregated model to predict post-chest X-ray oxygen requirements. And the results they're showing their Nature Medicine paper, that's the aggregated model performs better than any locally trained models. Okay, so this is I would say a vision from NVIDIA. So really, we talked about Rapids, MONAI, and BioNeMo. We really hope people can combine all those different modalities to enable some very important downstream tasks to make that a reality. Well, okay. And then moving towards the medical device side, right? We have Holoscan. It's a real-time AI sensor processing platform. So as you can see here, so many edge devices, edge applications can leverage the power of AI. They can be augmented by AI, right? And then Holoscan allows you to easily orchestrate and manage your end-to-end edge AI and also processing pipeline. And also comes with the hardware, the chip, and also the system to run it, to augment your edge system. And also, so one use case is to use it to augment the traditional microscopy systems, like this one done together with some labs at Berkeley. So this technology allows them to run their edge processing things, and not only just deep learning, but also other kinds of processing super fast. Everything is on GPU now, and then they can visualize in real time and also track interesting events under the microscopes. For example, when a cancerous cell is splitting into 2 or 3 cells. So we have a demo recording there on YouTube. You are very welcome to check it out. Okay, and then moving to the robotic system. Well, there are so many different types of robotics. We can use robotics for imaging and diagnostics, right? And also for the OR room, and also some humanoid robots, right? Maybe you can, I definitely believe one day we will see those humanoid robots roaming around in hospitals or maybe in the research labs, right, to help us carry out some tedious tasks so that we can live a better life as humans, right? Okay, and then so you can see Isaac. It's a robot's physical AI training framework. Now it's starting to support more healthcare related use cases. Yeah, for example, synthetic data generation, and also those robots need to learn from human demonstration, right? And those kind of things are really making those kind of surgical. We internally we call it stabby robots, like into a reality, make them possible. Yeah. Okay, so I have blah 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 a lot about the AI age we're in and what NVIDIA is doing, and specifically what NVIDIA is doing for healthcare. Now let's dive deeper into the solutions for digital health. Okay, we're gonna introduce all those technologies one by one because they're built on top of each other. First question first, what is large language models? Well, according to the official NVIDIA glossary, large language models largely represent a class of deep learning architectures called transformer networks. You don't have to understand what is transformer networks. Essentially, it's just layers of like neurons, and then they're trying to putting them together and try to model something. So it's just a very sophisticated mathematic function. You can think in that way that we humans cannot analytically write them out. So that we just put together something very many layers, put lots of parameters that can be learned from our data, and then we just let it to figure out what is the best parameters to put for each of the positions there. And by that way, theoretically, we can learn, we can do the mapping from any like input to any output domains. So yeah, but you can definitely check it out on NVIDIA's glossary website to see what are those networks. So for now, that's good enough for our understanding. So what is more important for us today, that what are the use cases for those LLMs, right? So here are listed some very feasible use cases today. For example, content generation, for example, story writing, marketing content creation, summarization. They're super good at that. And translation between languages, but also between the text, human languages, between English to maybe Python code, and also classifications or chatbots. Very feasible, very viable use cases. Okay, so now we have a basic understanding of LLM. What can we have some concrete, very viable applications of applying LLM? Well, there is definitely one, and I really want to emphasize this to you today. It's called Retrieval Augmented Generation, or RAG. So why RAG is very powerful and very popular today? It's because it can provide us with context-aware responses so that we don't have to retrain our LLMs again and again once we have new data. Instead, actually, we can just connect our already trained LLM with our own internal, maybe proprietary databases. And we ask the LLM to answer our questions based on our own internal databases so that we can have less chance of having those LLMs hallucinate. We can have more accurate answers from those LLMs. NVIDIA actually put together a blueprint, which means you can deploy it very easily. I'm going to show you the real websites in a bit, but let's just look at what are them, like at a high level, what's the diagram looks like. So essentially it has two parts. The first part is the extraction pipeline, where we are building our own vector database. We need to build our own vector database based on our internal data. For example, maybe some PDFs from my last literature review, right? And then the second pipeline is called the retrieval pipeline. This is where we can actually leverage use of this RAG application. So let's first look at the extraction pipeline. What is happening happening. So let's say I have 100 PDFs that I downloaded from PubMed last month. Okay, and then I embed it into a vector database. Okay, so why do I need to embed it into my vector database? Because then I can do semantic search within my vector database, and it's required by the current RAG technology. So how can I embed my PDFs? Well, in PDFs, they have different formats of data. Some are just text, some are tables, some are charts, some are infographics, right? And NVIDIA has all those microservices for you to extract all different kinds of information, and then first convert all of those kind of information into text or metadata. They are all text. And then we embed them into my vector database. So embed here really means I'm convert my text, my English text, into some English into the numerical representation. So, for example, I have one sentence or one paragraph from one paper, and then this model, it's also a neural network, can convert it from the text space into a vector. A vector is just a numerical representation of this originally a text paragraph. Okay, and then I embed it. And then, so I'm going to do it for all of my data, my 100 papers, and then I'm going to build this database for it. I'm going to index it, make sure it can be easily searched through. Okay, then once I have it, I can actually leverage this RAG pipeline, the retrieval pipeline. So maybe I will ask a question. So the question will be called a prompt. Maybe I want to add some guardrails around it to prevent users from asking invalid questions. And then I will also go through this embedding, exactly the same embedding models to convert my own question from English space to the numerical space. It will essentially become a vector, a series of the numbers. And then I will use that embedded vector to do similarity search within the vector database so that I can find the most relevant data or chunks of data from my own vector database. And then after that, I will use another neural network to re-rank all those finded chunks, okay? And then I will only use, for example, the top 5 most relevant chunks and throw that into the LLM, and also throw my original prompts into the LLM to make sure the LLM is aware of the context from my chunks of data, and then give me the answer. Hopefully, it's much better than the one without doing the RAG. Okay, so, and then when it spits out the answer, you might also want to add some guardrails to keep it on the topic, for the filtering out other non-relevant stuff or toxic stuff, and then give the user the response. Okay, so this is what essentially what is happening under the hood for RAG application. Okay, so the RAG techniques can be applied to so many different use cases, and NVIDIA has this generative AI example public GitHub repo where we put all the codes and descriptions about how to use them for each of those use cases. And today I really want to focus on this use cases, which is AI agent. Okay, so like I have already alluded to you, the emergence of a specific type of LLM, which are called reasoning LLMs, are really empowering our AI agents. So how is that reasoning LLM different from the traditional LLM? Well, they have this capability of break down a complex problem into smaller problems, and then it can tackle each of the smaller problems automatically for us. It can also reason through the question we asked it, and then it go through many steps. Sometimes people call it long reasoning to figure out what is the best solutions. It's so that you can see, it's very powerful. It can help us with so many different things. So essentially, when we are using a reasoning model to build our AI agent, it can help us to plan. So for this big complex problem, what I need to do, maybe I need to calculate something. I need to search from the internet. I would need to generate something to test it out. And then also reflect on that if it's good or not later. And then once it develops a plan, it will call the most appropriate tools to solve those smaller problems. Okay, maybe it is to do a web search, maybe it's to call a calculator, maybe it will call our RAG pipeline, right? Just we just showed you. And then once it gets the initial result, it will critique itself by itself to see whether it's getting a good answer or not. Okay, and then can iterate through. So this is how powerful those reasoning model-based AI agents can be. Okay, so because they are so powerful, NVIDIA had already built a blueprint for that. It's called AIQ. So essentially, it's a research assistant AI agent. Okay. So it shows how to connect those AI agents, reasoning models, our own data, and also tools. So let's take a look at the high-level diagram. So this is me, the user, and I can talk to my agents. And the agent, because it's powered by the reasoning model, it can do planning itself. It can reflect on its own results, on its own in silico experiments, and also can refine its own results. Okay. So for example, this agent today can automatically help us do web search, and also it can help us to call the RAG pipeline here. You see, does that now seem familiar to you? Like we have our own databases, right? Vector databases. We embed all of our things. Yeah, so this is the RAG component there. And then after that, after it leverages those two different tools, it can get the results and also generate a report and get it back to me. Okay, so this is the AI agent for research assistant. It's very useful for doing literature review and then to ask the AI to help you generate some hypothesis. So now I want to give you even like more adapted use case of those research assistants. So, in the drug discovery domain, they also have tons of literatures which are very hard for humans to keep up with every day. So what they're doing, so actually it's NVIDIA has already put together this blueprint to build a biomedical specific research AI assistant. Okay, so under the hood, this is actually a multi-agent system. Okay, so let's see what are they. So the first one is the literature search agent. It's actually under the hood using a RAG pipeline. And then it also has a research reasoning agent to help us generate a useful hypothesis based on the results served by this literature search agent. And then after that, they're calling another agent. It's called virtual screening agent because, in drug discovery, they need to always dock their target protein with some potential small molecule candidates as therapeutics together. And doing it in wet lab is very expensive. So they did better to do it in silico, in the dry lab first. And after doing that, we have another agent called report generation agents to help me generate a report of this whole process. And after that, me as a researcher can chat with this real-time chat agent. It's actually also a RAG system to reflect on the results from this dry lab, right? And also reflect on everything the literature search agent find from the web internet, so that we can reason together. Okay, now I'm gonna show you a recorded demo about this agent. So this is the UI interface, right? On the left side, it's just the interface where you want to input some questions and get results, chatting with your agentic systems. On the right-hand side, those are the tabs that you can view. So the first one is we're gonna do this literature search. So let me play this demo. So first, input our question, right? So this question, you can see, I'm a computational chemist, and I'm studying this cystic fibrosis, which is a disease, and then help me to find some small molecule recipes. Okay, and once we click it, the first agent will be called, which is the literature search agent. It will find the remember the RAG system? It's essentially the RAG system. It will find the most relevant chunks of data from my own literature databases. So in this case, we actually compiled over 60 different publications in that domain to build our vector database. And after that, the result will be fed into another, which is the reasoning LLM here. It will generate those hypotheses, some possible hypotheses for us to try out. So you can see this text think, it starts to reason. It will always use like first, next, then, right? And it will actually come up with some suggestions about small molecules. And after that, the suggested small molecules, right, and then and also the target proteins that find out will be thrown to the third agent, the virtual screening agent, to dock them together. Okay, calling some bionimal models to dock them together. And after that, we can go to the research report section to see the recording of this whole process. Like hypothesis, virtual screening, what is happening there. And then the next step is to go to the logs. If you want, like to see what kinds of agents are called, maybe this research literature agent is called, generate and dock molecule agent is called there. Then finally, if you want, you can actually chat with your results, right? So for example, here, we can ask some questions. What organs does this disease affect? And then this is another RAG system will help you to answer based on your literature review and also the results from your dry lab experiment. Okay, so I know like this is not the you guys are not doing drug discovery, but this is, I hope it's still inspiring. Like you can modify our AIQ and then customize it for your own purpose. So what is very exciting for me, from this agent is that all of those agents used, all of the large language models used by those agents, they are not customized for this specific domain. They are just out of box, off the shelf LLMs available today, So I really see this as a low hanging fruit for leveraging the power of agents and also LLMs. Okay, so the next step, since we already built some research assistant agent, why don't we make a human-like avatar? So NVIDIA has this technology called digital human. As you can imagine, now we have a very smart brain for this avatar. Then we need to add some appearance. For example, we want this avatar to hear from us. That's why we need to we would need to deploy this automatic speech recognition model, right? And then we can do some like RAG stuff as its brain, like also reasoning model as its brain. And also once it gets the results, we want it to talk to us, right? Instead of just typing out those texts. Well, we need to use text to speech, the AI like that. And also we want it to have a human-like face, right? We can use NVIDIA's audio to face 3D to give us lifelike lip sync and facial expressions, right? And then we also need a very powerful renderer from NVIDIA Omniverse to render it in real time. So actually I want to go there now to show you how to do that. You can actually try out later for yourself. So let me I think James is still not working well for now, but Ira it should be working now. So I just choose that. Okay, done. So click to speak. Okay, just give it a second.
I'm happy to help with any questions about NVIDIA's products and technologies.
Okay, so hello, how are you doing today?
I'm doing great, thanks for asking.
What's your name?
I'm Aria Gill, a digital human and analyst in San Francisco.
What kind of questions can you help with?
I can help with questions related to NVIDIA's products and technologies, including data center solutions and GeForce gaming products.
So what types of NVIDIA technologies were used to build you, like an avatar?
I was built using NVIDIA's Omniverse Avatar Cloud Engine, ACE, which leverages various NVIDIA technologies such as Audio 2-Face 2D, Riva Parakeet for STT recognition, and Llama 3.8b for response generation.
Thank you so much.
You're welcome.
Yeah, okay, I will just stop here. So feel free to play at your own time. Let me actually close this one. Okay, go back. Okay, so now we just go through this pipeline, right? Real time, I can get our using RAG to retrieve the knowledge from a NVIDIA specific knowledge database. And in the future, you can imagine we can add more agent or agentic workflows to those kind of avatars, right? Okay, now comes to this part, use cases. I compile some use cases for you to just inspire you to think about how you want to apply it to your own research. So NVIDIA has been collaborating with University of Florida because they are just as lucky as you guys. They also have a super pod there, and they built together world's largest medical clinical language models. It's called Gatortron. So they assembled the largest clinical data set ever. Okay, so not only they have the data from PubMed, like public domains, but also they use their own health health data. For example, like clinical encounters, procedures, diaries, exam summaries, etc. And the result is that they achieve state-of-the-art performance on lots of benchmarks. And they didn't stop from there. They trained a synthetic generative AI model called Gatortron so that it can generate synthetic but also very realistic clinical notes for like researchers in this domain, so that people can generate lots of data because AIs, they are just always hungry for high quality data. So like health data has their own like nuances issues, right? Like privacy issue. So easily generating those synthetic data is really, really helpful to further enable this domain. And then, NYU, the medical school there, they also get inspired by Gatortron. They train their NYU-tron. And then after they train it, they apply it to several different downstream tasks like 30-day readmission prediction in hospital, mortality prediction, also insurance like denial prediction. And they got very, very good results from using this model, and they call it all-purpose prediction engines. And they claim that they save tons of money every year for the hospital system. And then for multimodal sides of work, this is a work from Google's research lab. They're combining different sorts of modalities of data, for example, some demographic, age, sex, BMI, and also the numerical things like lab values, and also some time series data, like this lung function measures here. They embed them differently and then all feed them into the LLM to get very good high accuracy predictions for a disease for a patient. And then, in this domain, it looks like there are already several EHR-specific foundation models already built. And then this work actually examined the adaptability of some foundation models, in this case, a foundation model for EHR. And what they found is that this EHR foundation model can give very good performance compared with the locally trained smaller models. And it's more like sample efficient than those locally trained foundation models. So the lessons learned from that work is that, definitely first try to leverage those already existing foundation models before training something from scratch. That can help you to save lots of training budgets, and also the time and effort. Oh, and also, LLMs can be used to predict for future pandemics. So this work, they train a medical multimodal LLM, and then after they train it, they use multimodal. They train it. When they're training, they are not using COVID-19 like any data prior to COVID-19 outbreaks, and they applied it to the COVID-19 specific tests, and they find, well, after using a very small fine-tuning data set, like with very limited labels, they can help us to predict for like the unseen pandemics, what kinds of things will happen in the future. And also, like in the AI agents side of work, lots of people are starting to doing that. So this work, they are building some AI agents specifically for interacting with EHR databases. So traditionally, clinicians have to include some engineers, like bug engineer, all the time to interact with the EHR database. But now with this LLM-based and also specifically the reasoning model-based AI agents, the AI agent can help the clinicians to do so many different things, like database operations, code interface, like to generate some SQL code or some Python code, right? And also call all different kinds of tools. And also it can have its own long-term memory to really understand the context of the conversation. So yeah, and also in the education side of work, people are really interested in leveraging those like avatar, digital human, and also, of course, using some reasoning model under the hood to build some Gen AI systems for medical education. So in this case, looks like medical trainees are feeling less like confident when they have to handle some sensitive topics like the goals of care or end of life discussions. And to help them better prepare for those kind of things, people are now using like digital human and also reasoning model to generate those synthetic patient avatars and then to interact with the students. Like they actually generate lots of those kind of videos. And also, this is a more recent work. They are also using, trying to build this kind of synthetic patient system to help people like medical students and also for other kinds of downstream tasks. Yeah, and then this article is quite recent from Nature Biomedical Engineering. Looks like people are already envisioning, like in the future in the healthcare system, there will be so many different kinds of agents. Some of them, like on this grayish circle, they're gonna have very frequent interaction with the humans directly, and some other agents are gonna have less frequent interactions with humans. Yeah, so all sorts of agents. And then looking into the startup space, like some startups, they're trying to develop post-procedure care. Like people can just use their iPad and see the avatar there. And then some other guys are building medical concierge. So to provide personalized empathetic support through like voice, text, or live video, all leveraging NVIDIA's technology. And also this startup is trying to help people more efficiently schedule oncology-related clinical trials, like where I want to recruit more like participants, how to plan out my projects, how using the LLM's power to help people better plan things. And also for other like industry partners, or those are platform companies like Deloitte, Quantify, Accenture, they are all trying to build some very useful tools on their platform for end users. And also, like in our last GTC, it's a conference hosted by NVIDIA every year to make big announcements. So GTC stands for GPU Technology Conference. We also announced that our Epic is going to leverage NVIDIA NIMs on Microsoft Azure's cloud platform to build their own like AI-driven workflows from there. Yeah, so now it comes to the fun part, the hands-on parts. So to experience all the greatest stuff from NVIDIA, you just need to open up your web browser and type in build.nvidia.com. Then you will be directed to this NVIDIA's AI API catalog here. So let me quickly show you how to explore it. Well, you might want to see some like the rack example I have showed you. So it's actually here. So it's a blueprint. You can also find it under like the blueprints. So if you click on that, so you can see, yeah, our diagram, right? So, and the key features, and also what are the names used under the hood. Every names are laid out here. So for example, let's go to this re-ranking model. So here are the chunks, right? So those are the sample chunks, and here is a sample question where you can actually upload your own chunks of data and then your own question. Then once you click run, you will see it will be ranked according to this metric logit from high to low. Which means this is the most relevant, this is the least relevant thing. And if you want to try out this end-to-end rack pipeline, you can, but this is a paid thing actually. You need to click on deploy launchable, and then you will be directed to NVIDIA's own cloud platform called Brav. So Brav allows people to create templates of running something. So by a template, it means you will need to specify the compute you need, like the chips, the storage, and also the software stack. Maybe it's a container, and also the contents. Maybe it's a Jupyter notebook, and also you can export certain ports. And then you put them together, and then you can create a template, which is actually called a launchable from this NVIDIA Brav platform. And then you can click deploy launchable to build up this environment from bottom up. You just need to wait for it to be ready. But actually to use that, you need to put your own credit card there. So it's actually leveraging different CSP, cloud service providers, GPUs, and computer resources under the hood. Yeah. So this is the rack thing, but if you want to experience with any of those kind of models, this is completely free. Like from this web browser, you can play with it as long as you want. It's totally free, unlimited times to play with them. Okay. Now there's one thing I definitely want you to try out. So NVIDIA just released, I think several days ago, a foundation model. It's a foundation model for reasoning model. It's called NVIDIA Llama Nemotron. So we actually released it. We released the NVIDIA Llama Nemotron in several model sizes. This one is, I think, the largest one, so which means it's the most powerful one, and it's free to run within the web browser. And then you can ask it questions, and also note that here is a switch. You can enable the reasoning. You can also shut down the reasoning. So this is a unique feature from NVIDIA's Llama Nemotron reasoning families of models. Okay, so actually when I was preparing for this presentation, I have no idea what kinds of like use cases you guys might find interesting. So I actually asked this question. So how can like LLMs be used in epidemiological research? Okay, so I asked this question to help me, generate some hypotheses, brainstorm with me, and then it starts to think because I have this switch turned on. Okay, so you can see it step by step. And then at the end of the day, it will generate a report for you. You can actually compare the results when you have this on and off. Okay? Just give it a moment. Oh, by the way, so there are many open source reasoning models, but NVIDIA's Llama Nemotron model actually achieved the best performance among all those open weights reasoning models for many industry level benchmarks for now. Okay, so it's really leading, and also it's the performance, the inference performance is really fast. Okay, so let's take a quick look. Okay, so yeah, maybe you can use this for literature review and synthesis, right? I just show you that AI agent for research as a research assistant, right? And then for data analysis, interpretation, report generation, statistic guidance, and disease surveillance, event detection, risk communication, and yada. So many things. I was so happy when I saw that. I think, wow, you guys have so many ways to leverage those LLMs. Okay, I hope you can go through it by yourself. Okay, and then what's else? Well, I just want you to have some fun. So there's so many categories of LLMs, okay? Just have some fun. So for example, let me show you some ways. Okay, let me go to visual design. Okay, go to this edify image. It can generate, this is one kind of Gen AI, right? When I input some description, it will generate those synthetic images. So this one looks like the author is a dog person, but actually, like Maria already know, I'm a cat person. I have a pair of siblings, kitties. So let me see what will happen if I change the dog. I think so it's a happy middle-sized cat. And here, the dog looks excited with its tongue out. Okay, I'm gonna create some cats with tongue out. So the cat looks excited. Okay, so there are only 2 places. Okay, and then I run it. Yeah, so let's just wait for a minute. Yeah, if you look into those UI interface, you will also see, okay, there are many other things and the other parameters you can play with. Okay, it will control the uncertainty, like how creative the model you want to be. Okay, I got some very funny, right? You almost never see like cats like that, right? But this is one of the power of those Gen AI, right? It can generate so many funny images for us. I hope you can play with it by yourself. Okay, yeah, I think yeah. Okay, so if you are interested in like Monai, so let me just quickly go there. You can go to healthcare. So in medical imaging, we have 2 names ready. The one is for 3D Vista 3D. I'm not sure it comes back online because it was done early this morning. But yeah, definitely they will come back online next week, I think. So you can actually get all the automatic segmentations for over 100 different classes for your 3D CT volumes there. And also there's another one, it's called Macy. Macy is a Gen AI. So you can generate something static, but realistically looking images for certain body regions. This is actually using a differential model under the hood, so it's a bit slow compared with those transformer-based models. So, yeah.
Hi, this is super exciting. Thank you so much.
Yeah. Okay, I know it's already time. Yeah, sorry about that.
Would you mind giving us a summary and a wrap up, please?
Yes. I'm actually almost done there. So the very last parts, it's actually just a quick slide about resources for you to further your understanding of AI. So one is the one I actually just showed you, the build.nvidia.com. Play as much as you like, and also the generative AI examples. Like we put all some reference workflows there, and also if you want to watch something, then definitely recommend you to go to our GTC 2025 session recordings websites to watch some healthcare related sessions. So some of them are presented by NVIDIA's internal experts, like from the product team, how you want to leverage the tools. Some are actually from external researchers or industry users to present like how they're using those kind of things. It should be very inspiring. I really love them. And then if you want to get like more formal, like hands-on training, then I highly recommend you to look into NVIDIA Deep Learning Institute. So we have an amazing catalog of online courses. So it actually comes with 2 flavors. One is instructor-led ones. The other category is online self-paced ones. So yeah, you can look through that to see if there's anything you're interested in. So for example, we have DI online workshops for like how to do, for example, fundamentals of deep learning. And also when you want to scale up your model training, you can learn about how to do data parallelism, like splits your whole like gigantic data set across all of GPUs. And also you might also want to do learn about how to do agentic AI. We also recently have one coming online. all sorts of things. And also a video glossary is very, very useful if you want to get some basic understanding and some basic use cases. Definitely go to a video glossary to see, for example, what is Gen AI, what is physical AI. It comes with not only the explanation, but also the most popular use cases and point you to other learning resources as well. So that's it. Quickly summarize. So we have an overview of where we are in the AI age, and also where NVIDIA is contributing. And I hope the major section, the digital health, like the technical one for this session, is helpful for you guys. What is LLM and how RAG is leveraging LLM, how it gives us context-aware responses. That's why they're so useful. And we can always update our databases, right? And we don't have to retrain our LLM. And then how AI agents can leverage LLM just as a tool, but the AI agent can also leverage other tools, right? And then we showed you how to use a research assistance AI agent and then give them a human appearance, right? By using digital human. So that's it. Let's dive into the Q&A.
All right. Thank you very much, Huiwen.
Yeah, absolutely.